Good evening to all of you, ladies and gentlemen. And we are all set to begin with our panel discussion number 2. And the topic of the panel is going to be emerging nuclear technologies. And we are glad to announce that we have the session chair, the chairman of the panel, Shri P.A. Suresh Babu, Director HR of NPCIL, requesting Shri P.A. Suresh Babu ji to please come on the dais. Shri P.A. Suresh Babu, Director HR of NPCIL, as a chairman of the panel. Over to Shri Suresh Babu, sir.
Thank you, Prince. Already he has told it is the second, we are in the second day and the last session, and it's an important topic, emerging nuclear technology. It's a very vast topic, and the past 2 days we have been discussing, and everybody know that the nuclear energy requirements. I think absolutely there is no doubt that it is not like a requirement now. It is something like it's a must for the survival of the entire world. And it is also conveyed and discussed that we have even now, even in the, it was shown in the different, presentations and speak that right now the decision to increase the nuclear energy, it's by at least by threefold. That is to meet a decarbonization requirement. And there is another challenge which is also, very important, to take care of growing population and at the same time meet this requirement. With this, an important topic of this emerging nuclear technology, in my opinion, that the first and foremost important should be, I think all of you will agree that it is safety. Absolutely, there is no doubt that the most important requirement is the safety, right? And probably most important thing is, again, it's economy. That is also very important. So meeting safety requirement, economy, then how fast, because now the question is even, I'm in PCL and the question asked how fast you can build the reactors. Okay, so that is another thing, how to, any technology you bring, it should be more advanced technology so that our construction time can be reduced. That is also one of the most important requirement. And of course, now everybody expect that lesser, intervention from operator in case of any safety system requirement and other things. With this, I will, and we also know that emerging technology, when we talk about, I think this wall will be able to talk about now SMR, because a lot of discussion is happening in this room. I have seen about SMRs, and of course that is one of the important emerging technology. Same time, micro reactors, and we also know that a molten salt, high temperature reactors, fast reactors, and so on and so forth. So with this background, we have very learned speakers. So I would like to invite our speakers who is going to discuss with entire this, discuss about these emerging nuclear technologies. So I'm very happy to invite Ms. Valerie Faudon, Mr. J.R. Srinivasan, Mr. Ganapati Myenini, and Mr. Serge Gorlin. So let me, with whatever introduction we spoke, and let me start with get the views of Mr. Ganapati Myenini. Let me get the views of, in your, maybe it's, this is an introduction, you can speak about 2 to 3 minutes, and further we will, we will discuss and, we will proceed further. So may I request you to please give your,
Good afternoon, friends. Thank you for giving me the opportunity to express my views, personal views. The problem with the current technology is of threefold. One, it takes too long to build, it costs too much, and the spent nuclear fuel is a hazard for the humanity. And I think this is putting the goals of reaching zero carbon really in jeopardy. I think there are ways to circumvent all these issues. That can be done by implementing Dr. Homi Bhabha's vision of thorium usage. That can be done, in fact, right away in lieu of this three-stage program, not able to meet that. We can convert thorium, which is a fertile material, to fissile material using advanced accelerator technologies. So you add one neutron to thorium, which will transition to finally into uranium-233, which is fissionable. And the fissile products of this reaction are really radiotoxic for less than 300 years. So we are reducing radiotoxicity from hundreds of thousands to less than 300. That's one-fold. Take care of another issue. And these subcritical reactors can be built within 3 to 4 years. All the existing components need to be integrated together to make them operational. And I will be giving a talk Friday about all the details. Thank you.
Thank you. So yeah, I think you can straight away start. So that.
Yes, so as I presented this morning, there are really two fields of innovations I think are really fruitful right now. It's the new applications and also the new fuel cycle with the advanced modular reactor. So on the new applications, we've been working a lot in the French Nuclear Society on hydrogen. We published 2 white papers and we're going to publish a third one to actually show how competitive is hydrogen produced with nuclear. And we are right now working on heat and also working on spatial applications. So that's really very new, how we can use nuclear power to power deep exploration or future lunar bases or trips to Mars. So that's really, we're all very excited about that. And on the fuel cycle side, and I talked about this morning, actually used fuels for us are not waste. There's a lot of material in it and good things that we can recycle, and that I talked about plutonium this morning, but we have also in France a lot of depleted uranium that can power the country for several thousand years. Should we have the right reactor technology and be able to scale it up in an industrial manner. So I think that these are the two things that we're working on right now.
Thank you. Yeah, I think, okay. Yes, yeah, please.
I see 2 main reasons why the emerging technologies are emerging. About 2 to 3 decades ago, the only role assigned for nuclear power plants was power production. Maybe a little bit desalination was there. But once the seriousness of climate change was realized, and further it was realized that power sector is a junior partner as far as CO2 emission is concerned to other sectors, then the world thought that we have to tackle this issue. That's one reason. The other reason is nuclear industry is not static. It wants to learn from operational experience, accidents, and try to design so that accidents are either prevented or mitigated. In fact, I told the safety even during severe accidents in my presentation. The additional thing is they keep collecting the points which retarded its growth, like high-level radioactive waste management, construction delay, capital, economics, proliferation, public access with societal nuclear security, low physical footprint, compatibility with renewables, locating in urban areas, high seismic isolation, multiple applications like H2 production, actinide burning, transmutation, and special reactors were designed to solve these issues. Thus, the advanced and innovative reactors and SMRs were born. One thing which we have to notice is it's not only the reactor, it's the fuel cycle technologies which somebody mentioned, because we need accident-tolerant fuel and all those things. And even economics, trying to have a 24th month cycle. We can't generate 10 to 30,000 gigawatts required much later with the present day nuclear cycle. In fact, these technologies, it's a rebirth for them. Many of them are operated earlier, but the operation was not enough even to find out the bugs, leave alone solving them. In addition, the objectives of the present day reactors is much higher. So they have to go back to drawing board anyway, and that's what they are doing now. I have talked about challenges. I don't want to repeat because of lack of time.
I think we will discuss more details. Okay. So it's only a sort of an introduction. Yeah. I mean, then we will elaborate it further. Yeah, yes, please. Yeah, please. Yeah. Yeah, please. Yeah, Mr. Yeah, you can have a moment. Yes.
Yeah, thank you.
Yeah, Mr. Serge. Yeah.
So I probably will be approaching this from a different angle. Full disclosure, I'm not an engineer or a scientist, but I've worked in the industry for over 25 years, so I've observed a few things. There are brilliant scientists, engineers within this industry. We sometimes get accused of being not innovative, but I think that's far from the truth. At the moment there are nearly 100 different SMR designs that are trying to be developed. There are new approaches being researched in terms of accident-tolerant fuel, in terms of improving the back end, just to name some examples. I think the problem, I suppose, the angle that I will come from is how do we sort of enable, how do we get the fundamentals to enable these great, I'm sure they're not all great innovations, but I feel that a lot of these ideas are not sort of reaching the market, are not reaching industrial, because the fundamentals aren't there. A lot of the SMR designers say that their business model is based on, this is the point I raised in my presentation a couple of days ago, that once it's been licensed in one country, it'll be possible to deploy in others. NuScale already, if your business model is a global approach, and you're having to spend hundreds of millions in each jurisdiction, then those great designs are never going to reach the light of day. There's an issue with codes and standards as well. That's something that needs to be addressed. So digital innovation, which is essential. There are two main approaches to digital INC in the world, two main codes, and they have different definitions of things like defense in depth. So this is, I think, holding back emerging technologies. So, and the final point I'd say of introduction is and probably as a result of this situation we face, you see a lot of the main companies marketing themselves as non-innovative. So if you look at, I hope we had a presentation from Westinghouse about its SMR design, and I think they were emphasizing the fact we've done this. This is based on existing technology that's been licensed, and the emphasis is on deployability, how to deliver it. So I'll leave it at that.
Yeah.
Thank you.
Thank you. Well, I think from the initial discussion, I think it is all like everybody agree that, okay, of course, SMR is definitely one of the emerging technology, and of course there are challenges like fuel cycle, and we also touched upon like the importance of international cooperation, and also we talked about the importance of thorium-based reactors. Of course, I think many countries, including India, also, quite well progressed in that, and we also discussed about, quite important, like a fuel cycle, and also of course, in the hydrogen, I think I was seeing in the morning one of the presentation that the importance of hydrogen. So I think that is also going to be one of the, nuclear energy is going to be one of the, inevitable source to produce clean hydrogen. So with this, let us further go ahead, and probably I think since it is thorium is quite an important topic even for us, being in India and with vast we have enough resources of thorium. So I would like to start with to deliberate it more on thorium based reactors, and how fast probably we can discuss, and to whether we will be able to make a sort of a discussion and summarize that how fast based on the present the research, the developments, how fast a thorium based reactors can be deployed. So let me start with again Mr. Ganapati, because you brought this topic from your side. Yeah, please.
So I am aware of at least two systems that can actually implement thorium reactors. One is by the Copenhagen Atomics, based in Denmark. They are hoping to build a truck-based reactors, but the issue there is they have to start with a plutonium material to start the reactions. But I think they have some agreement with the United Kingdom, which has a lot of plutonium sitting somewhere, I'm not sure where. They are hoping to build it there very soon. And they are actually producing supply chains for molten salt, thorium fluoride, and lithium-7, etc. required for these kind of molten salt reactors that are walk-away safe in principle. Since these are molten salt, you do not need the containment domes and all the associated security systems, which make them time-consuming to build and also very expensive. So I think Thorcon is another company based in the United States, and I presented that system to be implemented in India at International Thorium Energy Conference 2015, hosted in this site, but there are no takers. And the current situation is that Indonesia has signed an agreement with Thorcon, and to build these kind of a modular reactors, the basic unit will be 250 megawatt, but the economics makes it to combine two of them in the basic unit that will be 500 megawatt electric, and these are based on, again, molten salt technology, and they can be built very rapidly, and we are expecting that Thorcon 500 megawatt units, first one will be built something around 2028, and it will come to the final operations within a year of that. And the capacity building of this will be constructed like in a shipyard fashion. So they can build 20 gigawatt plants in 1 year. So that is based on one shipyard basis type. So if you can establish many of those production facilities, you can ramp up this type of technology very, very rapidly. And the cost of these systems are really very, very low. 1 gigawatt plant that can be built in a year would cost about $1 billion. Think about that. And they are walk-away safe. So these are the two systems that the companies are working. But my corporation, BSE Systems, is developing advanced subcritical microreactors, and the capacity of that is 10 megawatt thermal energy, and which can be converted into other forms as required. And they can also be built by 2028 prototype. All the existing components can be assembled together. The neutronics of the design is done. It is going to be published shortly, so the details will be available to you as soon as the publication is out. It's under review. And we have done some economics of this ASMR. We call it Advanced Subcritical Microreactor. And it can replace in the United States industries that are using fossil fuel-based heat sources, we can replace them. And there are about 235,000 of those can be replaced with this technology very rapidly. And they can be produced pretty quickly as well. So this is where the status of this is. I will give you further details on my Friday talk.
I think, you gave a lot of input to our gathering here, and I'm sure I request all of you to whatever questions even I felt very, very interesting, and whatever questions you have, please note down. We'll have a session for all to answer your question of our experts who are sitting here. Thank you, and I request Madam to please continue with this. Of course, okay. I asked about your opinion about thorium-based reactor. If you have, not of that expertise, we can definitely, you can talk about, you talked about hydrogen, right? So you can talk about which type of reactors which will be more suiting for hydrogen.
Yes, so I talk about this request for proposal from our government for new companies to propose new designs, and we have 3 companies that have proposed molten salt designs. But as I think the gentleman was saying, in India you have thorium, and in Saudi Arabia they have oil, and in France we have a lot of depleted uranium and plutonium. So for us, we probably will use, if we use molten salt technology with plutonium and with chloride salts. That's really where the research goes, and there's investment in research from Orano and from CEA on fuel, basically PU, CL3 fuel, to go into the molten salt reactor. We see that as less mature than the sodium fast reactor, because we had in the past sodium fast reactors. So we do have a fuel design, and which is authorized by the safety authority. We just don't have anymore the fuel, the facility to build the fuel. So that's why I said in my slides this morning, I said it's different from a Gen 3 reactor, because in our Gen 3 reactor we will use the fuel, the same fuel fabrication and the same plants from that we're currently using for the EPRs and from the current fleet. But if we build a fleet of sodium fast reactors, we have the fuel technology, but we need to build back the facility to make the fuel. For molten salt fuel, it's more in the R&D process now. We don't have yet an agreed fuel with the safety of a proven fuel and with the safety authority. So it will be more a prototype work like the one they're building in the United States, McRae, something like that. McRae, they're building, a machine in the United States. It's more a research machine yet than a first of a kind. So if we start building that, it will be around 2030.
Thank you. Yes. Yeah. Yes.
Yeah. We talked about the bottleneck for AHWR. Something which is within our control is accelerator driven systems to convert fertile thorium to fissile U-233. Of course, if you put it in a reactor, you generate power. This will not be that, but this will at least make it faster. AHWR would have been a wonderful one. It will be a jump straight to stage 3. Now, some of the foreign developments which we have to consider, one is a Dupik cycle, which is tried in some PHWRs, but there are some fuel fabrication problems. If that can be solved, this is one use. Then I think Copenhagen Atomics have come up with HALEU and thorium. And the problem with this is if we import them, we have to put our reactors and safeguards. So some sort of a policy issue also will be involved. And there are, the use of thorium is being recognized world over now. A lot of developments. I think as time goes by, we should start either combining our research. We have a lot of research assistants doing together with France, for example, in their Jülich research reactor. So I think we should have a lookout. Ultimately, it looks as if only we may be worried about thorium. Remaining people are not bothered too much. So we have to be the, what you call, sheet anchors or beginners or the emerging technology in thorium.
Thank you. And you can continue, Mr. Serge. So, I mean, the question is, again, we were talking about the advancement and, implementation of thorium-based reactors. So, if you could...
I've confessed this was the kind of question I was worried might come up in the panel because it's not an area I've studied in depth. I've learnt about it, of course, and I suppose all I can do is emphasize that, think in a business-minded way, all those that are looking at. I know there are a lot of technologies developing that are thorium-based, and it has, and I know of its advantages. So don't underestimate. I think the SMR, some of the SMR manufacturers are surprised that they are subject to the same regulatory rigor that some of the standard gigawatt reactors are, even though they feel the technologies they're developing are safer, more intrinsically safe, for example. So I think that just really needs to be thought about, not to lose sight of the deliverability of those designs and raising the finance, etc.
Okay. Yeah, thank you. Thorium. You said rightly. Yes. It's okay. Yeah. Yes. Okay. So thank you. And I think we got a little bit input. Of course, the topic is quite vast. But I'm sure that we got a little bit input about the advancement of thorium-based reactors. And I think he has given Mr. Myenini has given a good. In fact, expectation like by 2028. Am I right? So that's what. Yeah, that's good. And you also said that it will be like, the installation time is quite less. That's what you said, right? Okay, so I think it's a good input. Thanks for that. And let us go to another, because we have been discussing more on SMRs, and I think there are a lot of papers. So we will not discuss much on SMRs and micro reactors. Probably we can just discuss more on maybe high temperature gas cooled reactors, whether I think experts, anybody in this panel could, they can discuss about high temperature gas cooled reactors. Okay, fine. Yes, fine. Okay, no, I'm just trying to discuss like, different advanced reactors so that at least we can discuss and we can, that's the intent of...
Yeah, the advanced gas reactors, they are already have operated, and we have one in China right now. And so there is experience in industry running them. So they're really a proven reactor. We have also the technology is available to make the fuel. So they're a promising technology. So out of the 15 companies I mentioned in France, one is called Jimmy, and they have won the award from the government to develop a high temperature gas reactor, and they already have they're soon going to announce the first industrial client. One of the things we've been working on is that we have these companies that are very dynamic because they're really young, entrepreneurs and so. And one of the things we've been working on with them is the issue of how they talk to the general public. It's very, because they're going to arrive into new cities, new sites, not areas where we have existing nuclear facilities. So of course we have to prepare of what is the process to engage with the local communities beyond their customer, right? Because you have an industrial site who is interested in buying the solution, but then we have to engage with the local authorities, with the population, and so far the safety authority hasn't yet developed the process for that. So it's a whole program that we have to put, which is not only a technology program, but which is really what is our process to go to new sites. One thing that we've learned, because these are all private companies, so they have government support, but they're private companies. It's not something we are used to, because in France, everything which is nuclear is public and is government-driven. And so we feel some reluctance about seeing private companies arriving in this area, is to really engage that the government puts in place a program with a master plan, so that we have a national program of where it is that we need these new resources, and there is a process with the general public, with the safety authority for these new sites. I think this is absolutely critical, and we must not overlook that, because we can fail the arrival of these new technologies if we're not able to talk to the general public well. So that's something we're working on.
Okay, thank you. And what about Mr. Ganapati? Would you like to? Okay, fine. Thank you. That's okay. I'm sure Srinivasan sir will definitely have idea. And please, yes. Sorry.
No, there's something I wanted to say also, because because we have all these technologies, everybody's asking for fuel. And we have to think about the fuel, because I think that's really what happened in the United States, because you have, like, at some point 50 startup companies all developing exciting technology, and everybody was focused on the reactor. And at some point in time, people were like, well, what about the fuel? And actually the fuel is a very, very important part of this technology. So that's also something that we should be really aware of.
So the BSC ASMR will be a breeder burner in equilibrium, so it will produce its own fuel, and I think there may be enough uranium-233 to start this up. Even if that is not the case, we may take some time to breed the required fuel for this.
It's okay.
Yeah.
It's right. That's all right.
Yeah. High temperature gas cooled reactors, one of the two best reactors for decarbonizing hard to abate industries like steel, this one, because they can attain the good temperature for process heat. It's not that they were not there earlier. They were earlier like pebble bed reactor in South Africa and many others. But as I mentioned in my presentation, they didn't operate enough to unearth all the bugs. Right now, of course, it's one of the 6 reactors chosen by Generation 4 group. And so it's going to have a very strong rebirth. China has already put one high temperature gas cooled reactor in the commercial domain. So that's a good beginning for the world to do. The other reactor, I would like to repeat what I read. Molten salt reactors are worth their salt. So these are also high temperature reactors, and they have so many advantages. Like I mentioned about ERO-EI of 2000, and they are simpler, give high temperature, good nuclear cycle facilities, simpler high-level radioactive. So, of course, India is also developing one now. So these are the 2 reactors which I see will be there for years from now for decarbonizing non-power sectors, mainly supplying process heat and other things. So,
Mr. Siggi, would you like to comment on this topic? Yeah, please.
Very briefly, because I think it's just covered some of the points I was going to make, but I think it always it has struck me as slightly strange that this high temperature gas cooled reactor is Gen 4, and at the same time was being developed back in the 1960s. And I had the privilege of interviewing a gentleman who was involved in the Dragon project at Windthorpe. And a lot of those, I suppose I'd like to make the obvious point that as we develop nuclear that we should be leveraging the research that was done in that period, when really there was, if you look at the investments that were made, relatively speaking, there was so much more up until the sort of 70s, 80s, and so we can, but it's very good to see that's still being utilised. The South Africans obviously put a lot of money into developing PBMR and didn't get off the ground, unfortunately. But then I think there was some and I think that the South Africans used a lot of the German scientists that had been developing that had sort of carried forward the silicon carbide fuel concept, and then I think in turn the South Africans have been cooperated with the Chinese, and as you say, there's this plant now at Shidawan, which I know it was delayed, but I believe it is operating now, and I'm interested to hear if it's still, yeah.
I think it was very interesting to hear about your interview you had long back with the person who was directly involved in that. Yes, good. And I think let us move on, and probably I think we were also talking about accident tolerant fuel, and I think we had some abstracts and presentation about advanced fuel cycle management, which is also very, very important. So I think this is also very important when we talk about advanced reactor technology. So probably I think we can discuss about accident-tolerant fuel and advanced fuel cycle. So this time let me start with Ms. Valerie. I think about accident-tolerant fuel and advanced fuel cycle.
Yes. So the companies in France, especially Framatome, has been very active with a new design of accident-tolerant fuel, which is actually tested in the United States. It has become a very strong topic for us because we have in Europe something called the taxonomy. Yes? Okay. We have in Europe something called the taxonomy for green finance, and it was decided that the nuclear would be included in green finance, which was a great victory for the nuclear industry 2 years ago. Took a lot of reports from experts to see that we were satisfying all the criteria, but actually in the decision from the European Commission, we have the fact that we have to use accident-tolerant fuel. So for 2 years we've been discussing what is it and what is the definition. So some argue that the latest fuels are accident-tolerant, yeah. Exactly, because they are better than the previous generation. But there are lots of discussion of do they exist, have they been agreed, licensed, what is the situation? So I think it's still not resolved. But it's true that's really a great moment of innovation. So it brings a lot of benefits. It brings new issues because, for instance, it's a new fuel for us to recycle. Typically in France we recycle.
And could you continue with advanced fuel cycle management also, if you could?
You mean the fuel cycle, the way we recycle in France? Yes. Okay, so we have a plant in La Hague, where we take all the used fuel in France. All the used fuel is recycled. And so what we do is that we separate in a used fuel, we separate plutonium, which is 1% in the used fuel, reprocessed uranium, which is 95%, and 4%, which is final waste. So the final waste is retified, is right now stored in La Hague, and we're building the deep geological repository, which will be a clay repository, which will take this vitrified high-level waste. And right now we are in a process of getting the licensing from the safety authority on the design of the final repository. So the 1% uranium is today recycled. We mix it up with depleted uranium, and this MOX fuel today produces 10% of our nuclear electricity in France, so it's pretty good. And for a while we had stopped the use of reprocessed uranium because uranium was cheap, but natural uranium was cheap, but now we have decided to start again. So we have the Cruas plant in France, which this year has loaded, I think, is loading right now, a new batch of reprocessed uranium. And so we plan to extend the use of reprocessed uranium to other plants. So that means that we'll reach the number of 25%. That means 25% of the electricity produced in France will be produced with recycled material. So we're very proud of that because we have this objective of circular economy in our fleet. But of course we can go further than that. We could also start, we have now a lot of used MOX. So we are building a big new pool to actually store this used MOX, but we're looking at solutions not to recycle the used MOX. So first we know how to basically separate used MOX, but we have two options. One option is to do a MOX2, which would be a solution that would go into the future EPR2 fleet. And the other option, of course, is to go to fast reactors. So these two options are on the table right now and are being looked at.
Oh, thank you. Very interesting. I'm sure a lot of questions can be expected on this topic. Yeah, thank you. And sure. Yeah. So, would you like to add on this? Anything on your opinion? Yeah, sir. Yeah. So I asked 2 points. One is accident-tolerant fuel, and second one is combined with advanced fuel cycle, like using, which Madam has already explained, right?
Yeah.
Yes, please.
Many countries in the world are developing accident-tolerant fuel. I think the Russians call it by some other name, but the final purpose is the same. If you analyze the 3 accidents that have taken place, it's mostly due to metal-water reaction, which has augmented the seriousness of the things. So one is to go away from this metal-water reaction or zirconium-water reaction. So they're testing many materials which does not have this reaction. The main objective is, in case of severe accidents or design extension conditions, there should not be any problem in the public domain. Of course, if you write up the reactor, it's something else. It's an economic penalty. But there should be nothing which requires any countermeasures to be taken in the public domain. Of course, one would have liked faster development of these things. Many times I've read somewhere that we are trying to solve a 20th century problem in 21st century with a 22nd century solution. So we would like things to be fast, but nuclear engineers realize that it has to be going to RDDD, development, research, deployment, and commercial domain. So it takes time, but some of the things like, for example, EU taxonomy straight away says that ATF is a must, which only make the people to hurry up, but they may lose quality and this one. And the other thing,
I asked about
the thing
like
is
fuel management.
Yeah,
like,
the fuel cycle development. There are many issues with fuel cycle. Of course, important is non-proliferation, and also how much high-level radioactive waste it produces. And then, of course, megawatt days per ton burn up. Then again, for LWRs, unlike PHWR, which has unpowered fueling, what is the fuel cycle? Like, is it 18 months or 24 months and all this? So I think these are all being addressed. Of course, high-level radioactive waste is being separately addressed also. And these are the things, so the research is on the whole fuel cycle, not just fresh fuel.
Yeah, okay, yeah. Yes, Mr. Zegi.
Thank you. So, well, we were talking in the last question about silicon carbide fuel, which of course is very accident tolerant. It's but when we come to the vast majority of fuel, of course, is described with zirconium cladding, and it's really encouraging to see the developments. And I think I understand that there's a need for some of the utilities to step up and offer their reactors for the lead assemblies, and I think that's really an area where the industry as a whole can collaborate, because I'm not sure what advantage the utilities always want to run their reactors round the clock. They don't want to, they're risk averse. So I think it's great that the generators of nuclear are willing and are stepping forward to say, yes, we'll test out those lead reactors that have, that are being developed by the fuel manufacturers that have enhanced safety features. Another question, looking at the sort of the full cycle, I mean, the question is being raised about, well, what about recycling accident-tolerant fuel that has, I don't know, some sort of coating, or is that going to work? And I was encouraged I know our colleagues at Rosatom have started to do research on that. I believe they may even have done a recycling batch with it, and the results were quite positive. But it's, again, that's good news for the whole industry that we're thinking not just about running them in the reactor in a safer way, but the whole fuel cycle is still, it still works. Just the last point I noted down here is that in our organisation we look at the once-through cycle as a valid option. That there are countries that are decided for their reasons, such as Finland, Sweden, and I think Sweden may be looking again at it, but Finland certainly has developed their deep geological repository on the basis of fuel once through, and that that is one potential option for those countries to deploy nuclear energy. We're quite sort of neutral about the different technologies. What we do say is you have to have a plan. You have to develop a plan, whether it's once through or recycling. But otherwise, there are different approaches.
Yeah. Well, I think it's. Yeah. Yes. Please. Yes.
So United States is doing only once through fuel cycle. There is hundreds of tons of material sitting, which is radiotoxic. It is being stored at the reactor sites, and the public is very much concerned about it. There is a lot of reaction from that. So they show up in these meetings and they keep asking these questions. So, well, people ignore it. So we continue this.
Yeah, well, again, it depends on the policy of the respective country, and yeah, it's fine. Okay, so I think let us.
The United States has planned to do the deep geological storage. Years ago, around 1995, there was a big news article in New York Times. A friend of mine, who is known as Charlie Bowman, is responsible for creating that. Otherwise, they could have started the underground storage of this, but that's the reason why it failed in the United States. One single guy could interrupt the whole planning.
Yeah, well, I think we have we have another, maybe we can take another 10 minutes and then the forum will be open for all questions and interaction. So I think I would like to maybe even touch upon a bit on fast neutron reactors. Probably that is also one of the emerging requirement. Of course, there are operating stations. Even India itself, our FPTR is operating more than 40 years, and our next reactor is getting ready mostly by next year. So I think we can discuss a bit about fast neutron reactors and what will be, how it will be emerging. I mean, advancement in that area. So let me start with. I'm talking about fast neutron reactors. Yeah. So let me start with. Okay. Oh, it's okay. Can you? So let me start with Srinivasan sir about fast neutron reactors.
Yeah. Again, fast reactors. It's a rebirth again. They were operating in 1947 or something, if I remember. For many reasons, I know the reasons, it just faded off. But now it's gaining importance. I think 4 of the 6 generation 4 reactors are fast reactors. Many type, I mean lead cooled and sodium cooled, and so it looks as if that if you want to have nuclear power until fusion comes, or even after fusion comes, for a long time to come, the present day cycles will not sustain. So you have to use thorium, you have to use probably even mine uranium from the sea. In fact, a large amount of uranium is in the sea, but it's not commercial now. So there are a lot of things which can be done. Of course, once fusion reactors come, then maybe these reactors will fade. So I think the fast reactors will be the in thing now, and of course we are frontliners in fast reactors. One day I hope with available thorium also that can be sent to countries who do not have fuel, we may be forerunners in export of fast reactors. And before that we have to establish itself in a very strong manner in the home ground.
Thank you. And Mr. Sigi, would you like to?
I think I'll pass on fast reactors. I think there's some more knowledgeable people here.
Fine. Okay, thank you. Okay, so yeah, we can start with you again.
Yes,
yeah.
So we have had several fast reactors in France, including a Super Phoenix, which stopped in '97, and that was a big disappointment for everyone in the nuclear industry at that time. So in last years we've been working on a project called Astrid, but the government has decided to delay the construction of prototypes on fast reactors because the priority right now is to replace the existing fleet. Because I showed this morning we have 56 reactors, but we still have no vision of whether they can go beyond 60 years. So if they cannot go beyond 60 years, we'll have to really accelerate the building of new EPRs. And so the priority is really on this capability for the security of supply of the electricity. I mean, the industrial priority. So as I said, the government has taken another approach, which is said we have some time now before we really start building a prototype. So let's open up to new ideas. And that's what they have decided. But among these ideas, we have at least 3 sodium fast reactor designs and 1 lead fast reactor design. So right now, some of them have already received support from the government to develop the ideas, but they are really innovative. For instance, the Hexana design, they're using molten salt to store the energy. So it's a little bit like the natrium design in Wyoming from what's the name? TerraPower, except that it's going to be a fast reactor. So because we have some time, they're exploring new and innovative ideas. And but we hope that, of course, we'll start building a prototype by 2018, 2030, and that will be able, based on this prototyping, to make an industrial decision for a fleet later in the 2030s. That's the dream we have, at least as a French nuclear society.
Yeah, it's very interesting. Would you like to?
There's nothing much I could say about it, but I can pass on a comment from Carlo Rubbia. So he felt that epithermal reactors are much better than fast reactors.
Okay. Well, I think you want to answer this.
This is more of a social talk. I want to take opportunity to thank France for giving FBTR to us. I think 40 years ago, and it's operating very nicely now. And in fact, it gave the impetus and laid the foundation stone for our fast breeder reactor program. I only a little bit upset that they themselves shut down Phoenix and Super Phoenix, but I'm sure they're going to regain on fast reactor technology.
Yeah.
Thanks.
Thank you. Yeah, that's very interesting. Thanksgiving, right? Okay, so I think we have a few more minutes, and let us before we summarize and get questions from them, let us, if possible, with time permits, we can just think of. We talked about all energy applications. Maybe if you can share, because of, like other applications of nuclear, because our topic is emerging nuclear technology. So maybe our panelists can discuss other than energy, whether we can, anything else, if you didn't, when you are expert. I'm very happy that is already coming. So we can discuss about other than energy applications of nuclear, Thank you.
Yeah, I think actinium-225 can be produced with the byproduct of thorium chain. Thorium-229 can be converted into actinium-225, and that will be one of the applications of our technology that we are developing. I think that's very useful, medical purposes.
Yeah.
Yes, so we also, we have some, believe it or not, we have stocks of thorium in France. And Orano has developed a process to extract lead 212 from these stocks of thorium. And these are being tested for alpha therapy in the United States. And they already have gone through stage 2 to cure some cancers. I forgot the name of whatever cancers, but I can find it. And so it's true that we have found a medical application for the stocks of thorium, and they are starting, we hope to commercialize this new alpha therapy really soon. Thank you.
Yeah, thank you.
This is a little bit of entirely new subject. Anyway, there are people know, especially people from BARC know the various applications. Almost any field you say nuclear energy is there. In fact, I was just wondering in this tunnel thing, they could have easily used some tracer technology to find out the best way to have reached them. And in fact, people say that nuclear causes cancer, but 60% of treatment in a Chicago hospital is by nuclear isotopes. So it is both the creator of the problem and solution to the problem. Innumerable uses, in fact, if a line gets plugged by something, they can know. Earlier days you have to really do a lot of navigation. Now they know by tracers they can find out exactly where is the problem. In fact, I think a BARC man can talk almost a whole day on various applications.
Okay, thank you. And would you like to comment?
Just to say that, there appear to be, there seems to be a lot of innovation in the medical area and the development of new sort of molecular healthcare. I think they talking about it now as opposed to nuclear medicine, at least in Europe. And just also perhaps to make the point that I think it's really useful for nuclear power sector to collaborate with other nuclear technology sectors. We've actually set up a forum recently. We've set up a cooperation forum for different nuclear technology sectors, and we want, because they face the same challenges that nuclear power does in terms of radiological protection rules, in terms of waste management, sometimes obviously not exactly the same in terms of waste, but there are definite synergies there, so we should be working we should be having a dialogue to see how we can collaborate better.
Okay, thank you. I think we have almost the topic which is of emerging nuclear technology. I think we have covered everything in a short time. Almost I think around 55 minutes. So we discussed, we deliberately we did not discuss much on SMR, of course, which all of you have heard a lot, and you are going to hear more on SMR. Other than that, we discussed about thorium-based reactors, molten salt reactors, and high-temperature gas-cooled reactors. We discussed, touched upon fast neutron reactors. We also talked about, accident-resistant fuels and the advanced fuel cycle, how to use spent fuel, recycling and extracting, and we discussed that. And we also touched upon bit on this emerging technology, which is non-energy applications also.